There's one last thing of the biological part that needs some design. As you know, nitrifiers need oxygen and also the heterotrophs. So you need to know how much air you have to get into the water to be able to convert all the BOD and nutrients. Therefore, I will show you some aeration systems today, as well as some rough calculations on needed capacities and energy use. Obviously, aerators are applied in the aeration tanks of the biological processes. Can you think of some processes in sewage treatment that need oxygen? Obviously, the removal of the organic contaminants, the respiration on BOD. Furthermore, oxygen is needed for nutrient removal, as you will learn in the next module. And last but not least, bacteria will die, decay and serve as food for other bacteria. This is called endogenous respiration, which needs oxygen too. The basics of aeration is based on the two-film theory of mass transport. As you can see from the figure, the mass transfer from the gas phase into the liquid goes via two diffusion layers, the stagnant gas film and the stagnant liquid film. We call this the interface between the two phases. The slightly soluble gases we focus on during aeration, like oxygen, encounter most resistance diffusing through the water layer. Therefore, the rate of mass transferred per unit area per unit time equals the overall liquid mass transfer coefficient times the driving force of the mass transfer. This is the concentration of the gas in the liquid phase when it's in equilibrium with the gas phase minus the actual concentration in the liquid phase. The equilibrium concentration is calculated with Henry's law, as is explained in the drinking water module on aeration. An equation that you might recognize is the mass transfer rate per volume instead of area. This equation is the one of the last slide multiplied by the area over which gas transfer takes place, divided by the volume of the phase in which the gas concentration increases. In our case, the water volume. The volumetric mass transfer coefficient, or KLA, depends on the water quality and the equipment. It is unique for each situation and is therefore always determined for each new installation. The KLA for an installation can be found by filling the aeration tanks with clean water. All the oxygen is removed by dosing sodium sulfite, whereafter reoxygenation starts by switching on the aeration device. The course of the dissolved oxygen concentration should be measured in time at several points in the reactor until near saturation conditions are reached. One can plot these findings as shown and find the KLA of the system. The oxygenation capacity of the aerator is the quantity of oxygen in kilos transferred in the total tank volume V. When respiration occurs in the aeration tank of a sewage treatment plant, we have to add a respiration rate to the mass balance. In this equation, it is expressed as R. In a steady state, the respiration rate can be calculated when the actual oxygen concentration in the bulk liquid is maintained at a constant level. Typical values vary from 2 to 7 gram oxygen per day per gram of biomass. The mass transfer coefficient is also temperature dependent, following the Van 't Hoff-Arrhenius equation. The temperature dependency coefficient lays between 1.015 and 1.040 and is typically 1.024 for diffusers and mechanical aerators. Since aerators are mainly chosen based on aeration efficiency, the alpha and beta factor have to be considered too. Since the mass transfer coefficient is often measured in clean tap water, It can change when the real activated sludge sits in the aeration tank. The alpha factor is a correction factor for this difference. Alpha factors for diffused aerators and mechanical mixers are respectively in the range of 0.4 to 0.8 and 0.6 to 1.2. Also, a beta factor should be introduced to correct for the oxygen solubility in activated sludge. This can differ from clean water because of presence of particles, salts, etc. Do you remember that I mentioned the oxygenation capacity? This is measured for the aeration tank in clean water and can differ when the tank is filled with activated sludge. Therefore, the alpha factor is introduced here as well. The actual oxygenation capacity should be at least equal to the total oxygen demand of the biological process times a peak factor. This peak factor is generally taken as 1 to 1.5 depending on the fluctuations in influent compositions and flow, tank characteristics and seasonal influences. Since you are now aware of the basic theory on aeration of activated sludge systems, I will show you some examples of different aerators that are often used in sewage treatment, as bubble aeration and surface aerators. Surface aerators function as giant whisks that you used in your kitchen to make sauces or whipped cream. Because they cause high turbulence and motion at the surface of the aeration tank, they are able to generate good contact between water and air. These surface aerators can often be found in carousel systems and mixed aeration tanks. They are very robust, but not that energy efficient. A special kind of surface aerator is the rotor aerator, that besides aeration also takes care of the motion of the water. These rotor aerators are often used in oxidation ditches. Finally, aeration can be performed with bubble aeration, placed at the bottom of the aeration tank. These can be designed as discs or plates, and they have in common that the fine bubbles travel from the bottom to the surface of the tank, which generates time for oxygen transfer. There are two types of bubble aerators: ceramic ones with the drawback of fouling and rubber ones. Due to the expansion of the rubber aerators under increased pressure, the holes open and air can escape. When the pressure is released, the aerators close themselves. This prevents clogging, while fouling can be removed by air bumping. Increase to a maximum pressure for a short while and then suddenly close the airflow again to break the fouling layer on top of the aerators. Bubble columns caused by the bottom disc aerators also introduce mixing in the aeration tanks, as shown in these pictures. Aerators can be positioned as uniform bottom aeration or as tapered aeration. With tapered aeration, one introduces lots of oxygen when it is needed, so when the BOD and ammonium concentrations are high, and less oxygen when it is allowed. Aerators are the main energy consumers of the sewage treatment plant, so to save on energy, one should use efficient aeration. Aeration efficiency is expressed as the oxygenation capacity divided by the overall power requirement in kilowatts. This efficiency includes blower and motor specifications and losses. Some specific values for surface aerators and bubble aerators are given in this slide. The efficiency of bubble aerators highly depends on the rising distance or depth of the tank. With this lecture, we close the module on basics of the design of an activated sludge system. Next module, we will continue with the nutrient removal processes. See you then!